We got one last idea here in 9.3. It's called the orthogonal trajectory of a family of curves. What is an orthogonal? That is quite a name. It's a curve that intersects each curve of a family at right angles. So orthogonal is another word we use for perpendicular. If two curves are orthogonal, that means where they cross at a right angle. So an orthogonal trajectory is, okay, you have a family of curves, um, but we're going to find the curve that intersects that family at right angles everywhere. And this is really interesting. At the end, I'm going to do a Desmos to show you just what this is like in the example, because it's pretty amazing, and it really makes sense once you've seen it, once you've seen the graph. Okay, here's what we're going to do. Here's our example. We're going to find the orthogonal trajectory for arbitrary constant k. So we've got y equals x over 1 plus kx. How are we even going to begin this? Find the orthogonal trajectory. Well, let's take a look. It's all based on being perpendicular, right? So we're going to start by finding dy over dx for that function. Why would we find dy over dx? Well, because that describes the slope. Okay. So this is our family of curves, right? K is like an arbitrary constant. Okay. Or it is. How is this connected to solving differential equations? We haven't seen that yet. Okay, it's coming though. There's our family. Let's find the slope associated with that family of curves. Well, here we're going to need a quotient rule. All right. dy over dx equals low d high minus high d low, all over the low squared. Not going to talk about any of those details. You guys are good with that. Let's clean that up a little bit. So it turns out we've got k times x minus x times k. So all we have there in the numerator is 1 over quantity 1 plus kx squared. There's our derivative. Okay, now here's where things get interesting. We still don't have a differential equation yet. We're getting there. We want to write this derivative in terms of x only. Okay, so right now we've got that k involved. We want to fix that. We don't want k here. Well, what are we going to do? We're going to write our derivative in terms of x and y. Excuse me, I should have said in terms of x and y only. And that's going to end up giving us the differential equation. How are we going to write this derivative in terms of x and y only? So, well, go back. We know that y equals x over 1 plus kx. We're going to solve for k, and we're going to plug it in there for the k. Solve y equals x over 1 plus kx for k and substitute. Now that's sneaky. Okay, I guess you could do that. Well, let's see here. Solve this for k. So we can multiply 1 plus kx over, divide the y. Okay. Subtract 1. And you guys are going to be seeing. Let's pull this up. Try and hide this work for now. Too distracting. So we're going to subtract 1. When we do that, think of it as y over y, right? Get the common denominator there. And then divide by x. And so we end up with k equals x minus y over xy. So we're going to take this and we're going to plug it into the x right here. Excuse me, the k right there. Wow, I'm just getting all mixed up. We're going to take what k equals and plug it in for k. Should give us this. dy over dx equals 1 over quantity 1 plus x minus y over xy times x quantity squared. There we go. That is what k equals in terms of x and y. And we're just going to clean this up as much as we can. We can see that x's cancel. So that's a great place to start. Just cancel those x's. 1 plus x minus y over y quantity squared. Okay, then we're going to go up to this side. What are you going to do with that? Let's find the common denominator between the 1 plus, and the rest of it. So we could think of that as y over y. So we've got 1 over quantity y plus x minus y over y, quantity squared. And this is really cleaning up nicely because y minus y cancels. So we have dy over dx equals 1 over x squared over y squared. And so we can stop right there. Dy over dx equals y squared over x squared. So we have, what is this? This is just the derivative of that original family, right? I mean, it's the derivative of this. Just really, rewritten and manipulated down very simply. That derivative, dy over dx, is y squared over x squared. So we have found the slope at any point, right, for our family of curves, or family of solutions. Once we have the slope for the family, we think, okay, we're trying to find the orthogonal trajectory. So that means we're looking for a curve that's perpendicular. Well, hey, if you know the slope, how do you find the perpendicular slope? How do you find the slope that would be perpendicular to it? Take the negative reciprocal. Well, the negative reciprocal here, negative x squared over y squared. This would be the slope for the curve that we want, which is at a right angle to this one. And what have we done? We have just created a differential equation that we can solve, which will give us another family of solutions. But the new family of solutions we're about to find will be perpendicular to that original family. Wow. What a maze this problem is. This is really exciting. So we found this is the slope of the original family. Here's this, and that's what we use, right? Like that was the bridge. Tell me the original family. Okay, then I can find the slope of it. Then I can find the perpendicular slope, and then I'll work backwards to solve this differential equation to find another family. Wow. Okay, let's solve that differential equation right there. Notice it's separable. We can multiply the y squared over here. We can multiply the dx over there. And we are off and running. Let me keep this on the screen. Solve this. Okay, multiply the y squared, multiply the dx. Integral y squared dy equals negative integral x squared dx. And this isn't going to be too bad at all at this point. 1/3 y to the third equals negative 1/3 x to the third plus c. And what we want to do is find an explicit solution because we want it to represent a function. So we can multiply everything by 3. So the 3, notice we are multiplying c by 3. It just so happens that 3 times c is still c, it's still arbitrary. And then we'll take a cube root, and notice that a lot of times you even see people switch these terms, negative x to the third plus c. Why not just think of it as c minus x to the third? You could keep it as the original, but this looks pretty nifty too. And then take a cube root. So the cube root of c minus x to the third, that is a family of solutions, and it will always be perpendicular to our original family. No matter what you pick for k, no matter what you pick for c, they're always going to be perpendicular where they cross, where they intersect. Okay, we're going to do a Desmos of that and a couple other things in the next video.